All right, so what we're going to look at today is what we call our ANOVA test. It's kind of a different looking name. And ANOVA stands for Analysis of Variation. You see the AN right there, the O from the of, and the VA from variation. So that's our ANOVA. That's where it's just an abbreviation for that. And today we're going to be looking at one-way ANOVA tests. And what this does for us is it allows us to compare 3 or more population means, right? So think about the testing that we've done. We've done 1 sample test. We've done 2 sample tests. What this one-way analysis of variation test is going to allow us to do is compare 3, 4, 5, or more means. Okay? And what happens is we're trying to identify if at least one of the means is different from the others. So our null hypothesis is that all the means are equal. They're all the same. Okay? That's the assumption, is that they're all the same. The alternative hypothesis, and I forgot the words at least here, at least one of the means is different from the others. Okay, so null hypothesis, they're all the same. Alternative is at least one is different. Maybe could be 1, could be 2, could be 3, but at least one of them is different. So then what is our conclusion going to look like? Well, if we reject the null hypothesis, it tells us that at least one is different. What it doesn't tell us, though, is which sample mean or population mean or which population means, if there's more than one that's different, are different. So that doesn't identify which are different, but at least tells us one of them is different. And why is this important? Well, let's say that we had 4 means that we wanted to compare. Well, if we're going to do a 2 sample test, what would we have to do? How many different ways can you take 4 different means and do a test for 2 of them? Well, that would be the combination of 4 choosing 2. And the combination of 4 choosing 2 is 6. Right? So that would be 6 different 2 sample tests to do a comparison with all of them. Okay? Now, that saves us quite a bit of work. But more generally, sometimes we wouldn't actually be interested in identifying which is different. We'd just say, okay, we want to know, are these all the same or are they not all the same? Okay? And then we can just do it with one ANOVA test if we don't really care which one is different. All right, so here are our conditions. Each sample must be randomly selected, this should say from a normal distribution population. Okay, so each sample, remember we're going to have multiple samples, 3 or more of them. Each sample must be randomly selected from a population that is normally distributed. The samples must be independent of each other. Each population must have the same variance. That's also important. And thinking back to what we've learned last from the previous section, we know how to test if populations have the same variance. So if we don't know that, we could run our tests from our last section to determine if the variances are the same. All right, so our test statistic, it's what we call our variance between the samples over the variance within the samples. Now, the variance between the samples is comparing one sample to the next. Okay, how do those differences, what do those differences look like, especially when we look at their sample means? Like, how different are their sample means? And then on the denominator, we have the variance within the sample, because we know each sample that we're going to take is going to have its own variance, its own standard deviation. So how much are each of the individual samples varying just within themselves? So the variance between the samples is sometimes called the mean square between, which we abbreviate MS sub B, mean square between. The variance within the samples we call the mean square within, MS sub W. So between, right, that's the variance between the samples, that's the numerator, and we put the B there. Mean square within, okay, that's the within the samples, we put the W there. Any questions so far? I know we got a lot to learn. How do we actually calculate these, right? And it's actually going to be, there's going to be significant calculations that I'm going to have to talk you through. So The test statistic, first off, we said is the variance between, that's the MS sub B, over the variance within, which is MS sub W, the mean square within. So this is how we find our test statistic, and we'll talk about how do we calculate the mean square between and the mean square within. Degrees of freedom. This is going to be an F distribution. Notice there's an F here. So this is going to come to F distribution. And from our last section, we know F distributions have to have degrees of freedom for the numerator and degrees of freedom for the denominator. For the numerator, okay, our degrees of freedom is the number of samples minus 1. If we're comparing 3 means, we have 3 samples, so the degrees of freedom would be 3 minus 1, which is 2. If we had 4 means we're comparing, that's 4 samples, so the degrees of freedom for the numerator is going to be 4 minus 1, which is 3. Okay. The degrees of freedom for the denominator is going to be the sum of the sample sizes minus the number of samples. So let's say that if we had 3 samples, 3 means, okay, 3 samples, and from our 3 samples, let's say the first sample, let's call it N sub 1, was a sample of size 6, and then our second sample was a sample of size 10, and our third sample was a sample of size 7. Okay. This big N is the sum of the sample sizes. It's the total number that were sampled. So for us, our big N would be 6 plus 10 plus 7, which would be 23. So in this case, 3 means 3 samples, and those are what we have. Our degrees of freedom for the numerator would be the number of samples, which is 3, minus 1, which is 2. And then our degrees of freedom for the denominator would be the sum of the sample sizes, which is 23, minus the number of samples, which is 3, that's 20. Okay, so that's how we get our degrees of freedom for the numerator and denominator. Now, let's go back to this. How do we find the mean square between and the mean square within? So here are the calculations. The first thing we need to find is what we call the grand mean. It's kind of fun. Look at this thing. Okay, it's like X bar, bar. The grand mean is we take all of the X's from all of the samples, okay, and we divide it by the total sample size, just like we talked about here. So what we would do is we'd take the X's from each sample, and we just find the mean of the whole thing. Even though we have different samples, we throw all those samples together and we find the mean of the whole thing. Okay, that's called the grand mean. Now, to calculate the mean squares between, we have to have the sum of the squares between. And to do that, remember this symbol, okay, means sum. Okay, and we had it right there. I kind of skipped over that reminder. But remember this sigma symbol means sum. We're going to take the sample size from a sample. We're going to take the mean of the sample minus the grand mean squared. We're going to take that, and we're going to add all of those up for each sample. Okay, it's going to make more sense when we look at our example for this video. The sum of the squares within helps us find the mean squares within, and it is also a sum. We take the size of each sample minus 1 times the variance of each sample, and we add up all of those for the different samples. Then to calculate the variance between samples, the mean square between, we take the sum of the squares between, which was this up here, and we divide it by the degrees of freedom for the numerator. To find the mean square within, we take the sum of the squares within, which is this up here, and we divide it by the degrees of freedom of the denominator. I know that's a lot. I'll walk you through each one of those. So, here's our problem. A sales analysis wants to determine whether there's a difference in the mean monthly sales of a company's 4 sales regions. We see them north, east, south, and west. That would make more sense. North, east, south, and west. Several salespersons from each region are selected and given their sales amounts in thousands of dollars. And again, this is for the month. Okay, so when we see this is 34 in the north region, that salesperson had $34,000 in sales. Okay, somebody else from the north region had $28,000 in sales for the month, and then somebody had 24, and then the same for the different regions. Okay, assume that each population of sales is normally distributed and the population variances are the same. At a 5% level of significance, can the analyst conclude that there is a difference in the mean monthly sales among the sales regions? Okay, so each of these regions has its own population mean. Okay, we've taken a sample, so they each have their own sample mean. We want to know, using the information from the samples, are the population means for each region the same or not? So let's just number our regions here. Let's call this region 1, 2, 3, 4. And again, for each of these regions, they have their own population mean, but we don't know what they are. Okay? And we're not going to find them. We're going to make a test to see if all those population means are the same. Okay. Now, before we get any further, let's make sure that we meet our conditions. So let's go back to our conditions page here. Each sample must be randomly selected from a normally distributed population. So when we look at this, several salespersons are randomly selected, and each population is normally distributed. So we've got the random, we've got the populations are normally distributed. Okay, so those two parts of number 1 here for the conditions are met. Samples must be independent of each other. Now, I didn't say anything about independence up here, but when we think about this, okay, is this region's sales independent of that region? Is this region's sales independent of the other 3, and so on? And I think we can say yes to the independence here because these are from different regions. How sales are doing in the north is not impacting how sales are happening in the east region, right? Because they're different regions, they'd be independent. So I think we have independence. And lastly, each population must have the same variance. And it says right here, population variances are equal. So we've got it. All right, our conditions. What is our null hypothesis? Our null hypothesis is that all the population means are the same. So that would be mu1 equals mu2 equals mu3 equals mu4. Okay. Our alternative hypothesis is at least one of the means is different. Okay. And the question is, can the analysis conclude that there is a difference in the mean monthly sales? So we'll call that our claim. So we want to know, are the sales performing at the same means? That's really what we're looking at. So we've got it set up. Okay, we're ready to go in our calculations. What I'm going to do is I'll conclude this video and we'll follow up with our calculations in the next video.